So today starts the transition to data analysis. There's going to be, it's not data analysis from now on, but today is, and we've got two excellent speakers, and the first speaker is Professor Alicia Sintes. Professor, yes?
It depends. For Spanish standards, no. For American standards.
Oh, okay. And I have the standard, embarrassingly long bio to read out, so I'll watch your face as I embarrass you. So Alicia did her undergraduate degree at the University of the Balearic Islands in Mallorca. And in 1996, she took a postdoc at the Albert Einstein Institute, the AEI, in Babelsberg, which then became the AEI at Golm, that a lot of people know about. And she joined the LSC in 1997 when it was first formed. So she was there at the beginning, and she was there when the first data analysis groups were formed with a very small number of people at the time, right? Yeah. And it was called ASIS back in the day. I can't remember what it stands for though. Alicia is currently the group leader on gravitational wave astronomy back at the University of the Balearic Islands. She joined that group in 2002 after her Marie Curie fellowships at the AEI. She initiated the group's participation in the GEO and LIGO scientific collaborations, for which she is PI at Mallorca. She's a member of the LIGO LSE Council, the GEO Executive Committee member, and since 2016, co-chair of the LIGO Virgo Continuous Wave Group. She's held multiple leadership positions in the gravitational wave field, as well as winning multiple awards for her scientific achievements. There are so many awards, and they're all in Spanish, and I won't attempt to read them. She has extensive experience in developing code for the LIGO Algorithms Library Software Infrastructure, otherwise known as LAL, and has pioneered parameter estimation studies for the space mission LISA. Together with her team, she is leading quick look searches for unknown isolated pulsars and spinning neutron stars in the data from the advanced LIGO detectors. So, is it embarrassing enough?
Yes.
Right. So, Alicia, you can get going.
Thanks, Chris. So first of all, thanks a lot for inviting me to Scotland. For me, it's a pleasure to be here. And when Chris or the other folks invite me, I say, like, of course I'll come. I'll make a gap in my agenda because I actually attended one of these SUSSP schools about 22 years ago. I was a PhD student at that time, and there were fantastic lectures. Well, I guess that all these Scottish summer schools are fantastic and excellent. But it was that time that I heard for the first time about gravitational waves. There were several talks from people from the Glasgow group, and I decided that I was going to finish my PhD in cosmology, but move into gravitational waves. And this is what I did, and I've been working on gravitational waves since then, basically. So I wanted to come here. Let's see what is this going to go, this lecture, but okay. I also met my husband at that summer school. That was in the whiskey distillery. Not so far away from here, in Aberdeen. That was also a good place. So, let's start. So, this lecture is the first lecture on data analysis, although you have already heard a few things from Satya. And it's going to have two parts. I don't know if each one is going to last 1 hour or not. The first is going to be a general introduction on data analysis, very basic stuff. If it's getting too boring because you already know everything, just let me know and then I just go faster. And then I'm going to start the first lecture on continuous gravitational wave. We are going to have a second lecture of gravitational wave next week by Professor Melisandre Papa. Okay, so what I'm going to be covering is in the first part, I'm going to mention a bit of blah, 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 that we are starting a new a new era in astronomy. What is this problem on data analysis for gravitational waves? And then I will focus, as I said, on continuous gravitational waves. I will talk about the sources, and I will point some of the strategies to search for them. So let's move. As you have heard, in principle, gravitational waves could exist at any frequencies. It all depends, well, we believe that there are no astrophysical sources higher than 10 to the 11 hertz. And basically, we consider that we can do direct searches starting from 10 to the minus 9 hertz. What is driven at what frequency sources emit, basically, as you know, are basically two main parameters. the mass of the system and how compact they are. The more massive the system is, the lower the frequency, and the more compact they are, the higher the frequency. In the high frequency, in the ultra high frequency regime, basically you have no apparatus to search for them. Don't even know, there could be some things, some strange alternative theory, whatever, that predicts several things. But here, between a few hertz and several kilohertz, is the band that it can be observed with the ground-based detectors that I will focus this talk on. So I will focus on sources for ground-based, so spinning neutron stars in my case, but it could also be, as you observe, binaries, stellar mass binaries, say the neutron star or black holes. And of course, there are many more sources and many other ways to look for gravitational waves. In the low frequency regime, you are forced to go to space, and I think you have more lectures about LISA and the space detectors next week. So I will not be covering that, nor the data analysis for that. The data analysis is also different for ground and space. There will be some differences. And if you want to be more interested in more massive things, more super massive black holes, then there's a possibility of using pulsar timing array. So you have full spectrum, and there are different sources emitting different gravitational waves. If we could observe these gravitational waves will be coming from sources characterized by the extreme physical conditions, strong non-linear gravity, relativistic motion, very high densities, etc. So because they are so extreme and so energetic, if we observe gravitational waves from them, they will help us to answer a number of questions that are important in different fields, in fundamental physics, in cosmology, and in astrophysics. You have already heard, like, it could be quite interesting in order to know how abundant are stellar mass black holes, what is the mechanism that generates gamma reverse, that I guess we'll have more talks next week, what are the conditions in dense central coarse galaxies and nuclei with massive black holes, how they form, what happens when a massive star collapses, and of course maybe even discover unknown phenomena, unknown objects that I cannot currently not even imagine. So to try to do tests of general relativity, study the accelerated history, the accelerating expansion history of the universe, etc. So this is quite interesting, important, and is completely complementary to observations that can be done with electromagnetic waves. On top, okay, you have heard, any accelerating matter can produce gravitational waves, but since even you can produce a lot of energy, the space-time is very stiff, and the amplitudes are tiny. So at Earth, we only have a chance with the current detectors and maybe future detectors, just to see gravitational waves produced by the most energetic phenomena in the universe, like the ones mentioned, or even the most energetic one you could imagine, like from the Big Bang itself, that is completely inaccessible from electromagnetic observations because the universe was not transparent to light after much later. So definitely, with gravitational waves, we will be able to open a complete new window in the universe. Now, the amplitudes, as you have heard of the waves, are small, and we are not talking about science fictions. This is currently being done. This might fly 2030, and with ground-based detectors, the way initially the resonant bars, there have already been a full initial network of detectors that were operating between the 2000 and 2010. That was compromising the LIGO detectors, Virgo, TAM, and GEO. And basically in 2015, started now operating the second generation, the advanced generation of detectors. The first one that started in operation, as you know, were the LIGO detectors. 4 kilometers arm length, one in Livingston, Louisiana, and the other one in Hanford, separated 3,000 kilometers among themselves. Second, that is currently, I think the official run, Chris? Official run will start, Chris will start August 1st, Virgo, officially. Okay, so in a few days, Virgo will officially join the current science run, and this is a 3 kilometers inland. Then there is the small Geo600. Geo600, even if it's small, is the German-British detector, with UAV also. That was the only one that was taking data between 2010 and 2015, while all the big ones were off. LIGO initially were 3 detectors. There were 2 in Hanford. Now in Hanford there is just 1. The third one is packed because it's going to move to India, and this is approved. So eventually this is going to be LIGO India operating in 2024. And in Japan, that there was Tama, then there was Clio, and so on. They are finishing basically another big interferometer, 3 kilometers on length, underground, the Kamioka mine, with cryogenics. So basically, they are start implementing 3rd generation technology. I guess they will start doing operations in 2018, and then maybe joining for science run in 19, and so on. Okay, so we have detectors, and as I said, the first science run of these advanced LIGO detectors were 4 months long, from September 2015 to January 2016. Then the last day of November 2016 until August 25th is when it's going to be the second science run of the LIGO detectors, in which Virgo will join. The sensitivity is quite similar to the first one. And then there's going to be a big improvement of the detectors before the 3rd science run starts, that is planned to be 9 months long. And eventually later, more commissioning, more upgrades, until at least one reaches design sensitivity. And as you have heard, as soon as the 01 run started on the 16th of September 2015, this was the beginning of a new area because it was fantastic. For the first detector simultaneously at LIGO and Virgo side, this was detected just with 7 milliseconds of difference, and you can see in this time domain graph the shape, the form of this chirp. This data, this signal, arrived to the Earth, and in less than 3 minutes from arrival, it was already registered, processed, and automatically there were alerts sent to the collaboration. The code that analyzed this, that found this, was this CWB, coherent wave burst, so not much filtering, time frequency method. Curiously, this is the code is reviewed by my husband and others. And this was the result that was published several months later. And you have all seen and heard that these were the image and the sound during the press release that was sent to the public, where the LIGO director David Wright said, yes, we did it. We have detected gravitational waves. Okay, as I said, this marks important day. This was the cover page of Physics Review Letters, where it was published. Since then, gravitational waves have been a fashion. In our group, we celebrated a year later with a beautiful cake that looks good and it was tasting even better. And that has not just been the only discovery, as you know. This was the first thing that was discovered. But then last summer, we announced the second detector, and last month, the 3rd detection. And this has made possible because there is a big difference between the initial detectors and the advanced detectors. So here you have a sensitivity curve in which we compare the sensitivity that were these initial detectors, well, the LIGO detectors, having at the end of 2010, with the sensitivity curve that we want to achieve with these advanced detectors. We want to gain 1 order of magnitude, and also we want to improve the sensitivity at lower frequencies. So we want to increase the frequency band. This can be done, or this has to be, if you want to achieve this, clearly one has to reduce quantum noise, reduce Brownian motion, and to have better seismic isolation. And you have heard also the talk by Peter Salson that this is possible by increasing laser power, by using larger mirrors, introducing signal processing and, well, dual signal recycling things, and there was a big investment in the isolation, etc., etc. So, the big difference between initial LIGO and advanced LIGO, well, the curve that I saw is the design sensitivity, is not where we are now, it's where we want to achieve. Basically, it's like, okay, the input laser in initial LIGO was 10 watts. Eventually, we will be using 150 or 180 watts. Currently, I think we are using 25, 30. The mirrors, the size of the mirrors for initial LIGO were 10 kilos, now 40 kilos. Initially, we were single pendulums, now quadruple pendulums. Initially, they were suspended by steel, now monolithic suspensions. So there has been a big investment in technology and so on to be able to construct such sensitive detectors. But there are still a lot of challenges. We have to finish the building and installing of these advanced detectors. So we have to finish Kagra, we have to finish LIGO India. We are basically now commissioning these detectors in order to achieve the desired sensitivity. We also have to be understanding the detector and the data they produce. This is now a new apparatus. We have been analyzing the first 4 months of data. This is new data, new problems, new things are arriving. We have to understand that. We have to be searching data for the gravitational wave signals. And we have to use it for gravitational wave observations in order to extract information that will be relevant for astronomy, cosmology, and relativity. So the challenges here is that we want to detect these gravitational waves, but also we have to be able to disentangle all the information that these gravitational waves carry. And all of this, data analysis is extremely important. Data analysis, with data analysis we got all the additional detectors upper limits. So we have full legacy on results. And apart from having the detectors, that of course the detectors are very important and it's important to have a good sensitivity. It's also important the duty cycle or how glitchy the data is. It's also important the calibration to reconstruct our A channel, the data quality, but many more things connected when we want to do data analysis. We have to know about sources, about waveforms modeling and predictions that were presented by Mark, about astrophysics, fundamental physics, and we also have to connect with other messengers. We are not working alone. We have to connect with radio astronomers, optical, etc. And there is also another important part that is computing. So all these things is relevant for data analysis. So the rest of the talk, I will just focus on ground-based detectors, sources, and I will skip all the part of space and lower frequency sources or methods. So, in ground, the different sources that basically we could see are, for example, the continuous wave sources that I will talk, coming from, for example, spinning neutron stars in our own galaxy, coming from pulsars. Those can be isolated or in binaries, as for example in the case of low mass X-ray binaries. And this will be emitting continuous gravitational waves, almost monochromatic signals. It could be a burst types coming, for example, from supernovae. It could be these in spiral merging landings, chirping signals from the merger of compact binaries. Or we could have an stochastic signal, an stochastic background, that could have either astrophysical or cosmological origin. So basically here the message is that even in this band, from a few hertz to several kilohertz, we have different sources. Each of these sources is emitting a different kind of signals. Some are short, less than a second, sometimes minutes, sometimes continuous. For some cases, we have very good models, I explained yesterday, to search for them, and therefore we will be able to use the optimal search techniques, match filtering. From other ones, not. So we have to design alternative ways for searching for them, and then there are also the stochastics. And basically these, continuous waves, compact binary coalescence, burst, or stochastic, are the four big groups, the four data analysis working groups of the LIGO and Virgo collaboration. because their targets and their search methods are completely different. And of course, they will have more types of signals and methods and so on to be developed if you go to Lisa. Lisa will be like a different problem. And data analysis is a challenging problem. And they already realized in the 80s that that was not going to be easy. And why? Because our antennas are all sky sensitive. And they have this quadrupolar antenna pattern. When I'm talking about transient sources, I would need multiple detectors in order to derive the direction of the source. My detectors are broadband sensitive. I have huge data sets, very large data sets. I have hundreds of instrumental and environmental channels that I need to record. I need to study the quality of the data. I need to make sure that when I'm making the detection, it's not coming from the noise done by the neighbor. So this is a very old number, more than 10 megabytes per second for each detector. And on top, as you have heard, for ground-based detectors, we have low event rates. We have already announced 3 detectors, no more. And we have a huge parameter space, huge number of templates that we have to search over. So this is a difficult problem. Basically, our detector is going to register a certain strain that is going to be dominated by noise. Yeah, so I have my data that is going to benchmark a potential signal. And this signal is a linear correlation of the 2 polarizations. Now here, I've plotted basically some average here of the 2, F cross and F plus. And then, okay, you could add them together, the root mean square sensitivity. This is this kind of peanut shape. So this is a very broad antenna. So it's not like a telescope that now you want to study some sources there, you point it there, sources somewhere else, you point. No, this is more like a microphone. You get all the signals of all the sources from anywhere in the sky at once. And it's going to be in the software with the data analysis that we will decide that if we want to analyze a certain point of the sky or not. Then, in general, or should a signal arriving at the Earth will be generally seen by all the detectors that will be operating at the same time, assuming that they have similar sensitivity. The antenna responses of the different detectors, of course, depends on the time of arrival of the source and the sky location of the signal. In principle, we could be operating continuously, monitoring the whole sky. In practice, it has been, depending on the detector and the run, it could be 50, 60%. In the case of GEOS, more than 90% all the time. And of course, all the data can be archived, and this enables that we can process the data many times afterwards, a posteriori.
Is there a reason that GEO had such a high duty cycle compared to like advanced LIGO?
GEO has always been a beautiful detector. It has always have been, it is also, I'm not sure, more simple or more difficult. It is, in this case, we are talking about microsensor interferometers with fabric POR cavities. That's not the same configuration in GEO. GEO has delay lines. It's basically like a folded arm. And in GEO has always been like the prototype to test more advanced technology. So like this dual recycling that now is in advanced LIGO, that was already there in GEO a long time ago. The monolithic suspensions developed in Glasgow, they were first installed in GEO. And the squeezing that will be implemented before 03 has already been demonstrated in GEO. So GEO has been a tiny facility, but a facility that has been demonstrating technology. So you have gotten a beautiful team of British and Germans working together that have done a great, great job. And it always has been the most stable detector. Do we have any experimentalists here in the room? Not really, they all escape. But yes, I mean, LIGO, initial LIGO was having duty cycles of 70%, GEO was in 95. Sensitivity is another business. With short arms, has to pay for it. Then, if we have a network and we are analyzing the data together, of course this allows us to be much more confident. And we'll be much more confident if the events are seen by multiple detectors. We can, as I said, infer sky locations and also separate both polarizations. And this, as I said, is a cooperative endeavor. The LIGO detectors together with the geodetectors, with its collaborations with the users, form the so-called LIGO scientific collaboration. More than 1,000 scientists in more than 15 countries and more than 90 institutions. And then the Virgo collaboration that I think about 250 scientists together with the LSC, they share all the data, they analyze the data together, and we publish together since many years ago. More benefits about having a global network. Well, first of all is the improved sky coverage. So as you see, we have this antenna pattern. So at a given time, for example, this will be like the average response to signal with a certain linear polarization with fixed coordinates, and this will be like the nulls, the places where you are not sensitive. And you see that the nulls are not located in the same place for the different detectors. With the LIGOs, they look similar because they are more close by, but in the case of Virgo, this has changed a lot. And for the network, this gets even better. So it's less likely that an event occurs in the null of the detector network than in the null of a single detector. So that's one thing for which it's important to have a global network. Then, if you have several detectors, you have an improved general duty cycle. So, in particular for transients, the things that we have seen, it's less likely that an event will occur when no detector is looking, it's operating. Then we can also increase our signal-to-noise ratio because we can coherently sum the signal from the multiple detectors and analyze them coherently. Of course, by having multiple detectors, we can improve detection confidence because multi-detector coincidence, for example, greatly reduce false alarms. And also we can develop coherent consistency tests that should be able to differentiate signals from instrumental anomalies. As I said before, also permits improved directional searches. There are many things that we can do. And sometimes it's like electromagnetic friends passing us signals, passing us triggers, at GRBs that I guess this will be also covered next week. And we can do also much deeper searches. Another thing is that as soon as you have 3 non-aligned detectors, you can do signal source reconstruction. And of course, the more people you have, you share best practice, etc., etc. Good, so let's move into the data. Okay, so the data is an instantaneous estimate of the strain for each moment of the time. In principle, for example, we are talking about the demodulated channel sensitive to the arm length difference. But as I say here, this is not the whole story, because this channel has to be calibrated, and I hope that some experimentalists will explain you all the business of transfer functions and so on, and how this data get calibrated, because this could be just a top by itself. The data is discretized, it's digitized. It's a discrete time series that is recorded in a computer. Okay? So, different times, we record our data. In the case of LIGO and GEO, the sampling rate is basically 16 kilohertz. In the case of Virgo, it's 20 kilohertz that are synchronized with the GPS time signal. Both collaboration, at least they record the data in the same format, what we call frame format. And we just not record the channel in which there is the gravitational wave signal. We record hundreds of auxiliary channels. Many of these also at this very large sampling rate. Now, our first question that one can arrive is that, is this sampling rate high enough? Well, let's recall the sampling theorem that tells us that the discrete sampling rates, can completely represent a continuous signal which only has a frequency quantum bit too low, the Nyquist frequency. So if you have to sample at least as twice the frequency of the signals that you want to that your data is going to have in. Okay, so what are the typical frequencies of the things we're interested in? Well, in the case of binary neutron stars and spiral searches, they could be up to 1 or 1.5 kilohertz. Neutron stars have modes up to 3 kilohertz. Black holes, quasi-normal modes, they will be around the 1 kilohertz for 10 solar masses black hole. So, okay, this is making a kind of sense. Core plus supernova can go up to several kilohertz, so that should be several kilohertz. Okay. And what will happen if the signal stands above this Nyquist frequency? Well, you're going to have the problem of aliasing. And that the data will be aliased down to lower frequencies. Either you might like it, or you have to live with it, or you have to correct it. So anyway, we have recorded the data, and this data will have noise, or will be dominated by noise. So this noise can have or not a number of properties that you have continuously heard, or you will continuously be hearing in this talk. One of the properties that noise could have is stationary. That means that the statistical properties are independent of time. And we could have also an ergodic process in which the time averages are equivalent to ensemble averages. For many of the theorems and for many of the things we do, we will be making this assumption, or that in some time scale the data is stationary. Not necessarily has to be. Another possible property of the noise is that the noise could be Gaussian. That means a random variable that follows a Gaussian distribution. If you just have a single variable, it means that it's going to follow this distribution. But you can generalize this to, for example, to a time series in which the is Gaussian if the joint distribution is governed by the covariance matrix in such a way that the probability distribution of this time series is just given by this. So the noise can be Gaussian. Maybe our noise is not Gaussian. The noise could also be white. What means that? That the signal power is uniformly distributed over frequency. That means that the data samples are uncorrelated. Or it could be colored. That means that the signal does not have the same power in a given value. And in general, we have that our noise is colored, just in the spectrum. And we might end up doing assumptions of a stationary and Gaussian noise, although our noise is not stationary and also not Gaussian. Definitely we see the difference of noise fluctuating between day and night. When we analyze data, most of the time we analyze data in the frequency domain. So our analysis is based on Fourier transforms. And then you all know the definition of Fourier transform, that it's a linear function complex in general that is defined from all positives and negative frequencies. But in general, we are working with a discrete, finite time series, and therefore we will be working with discrete Fourier transforms. And now starts the full mess of it. That, okay, this is a possible way to define a discrete Fourier transform. There could be others. In particular, where do you put the normalization? And basically, one thing that I want to mention here is like, okay, you can try to compute your discrete Fourier transform as you want for the frequency that you prefer. But basically, you're starting with n independent n data points in time domain. You only have n independent points of information. When you do a Fourier transform, you're only going to have n independent values. And if you know that at most this is going to span this bandwidth, what you can do is to analyze the Fourier domain, the Fourier transform at n equally spaced points. So this is spacing. The spacing is basically inverse proportional to the number of points you got. In particular, is 1 over the time of observation. Sometimes you need, or you want your, you are interested in knowing what is the Fourier transform, the discrete Fourier transform at intermediate frequencies, or with a much higher resolution. But we know that the Fourier transform can be very efficiently computed by the fast Fourier transform. So if instead of trying to see what math you have to do, one trick that is done by many of us is like if you want more resolution in frequency domain, what you do is that you zero pad the time domain. You just add zeros to make it longer and longer. You do the Fourier transform and then you go to over-resolve easy. So basically, I've talked about discrete Fourier transforms and continuous Fourier transforms. Depending on how you have defined, you don't get the same value. How they are related with the definitions I put up, basically, the discrete Fourier transform, it will be just the delta t, the continuous, it will be delta t, the discrete one, where the Fourier frequencies are just given by this thing here. If the starting data was real, then you all know that the Fourier transform have negative frequencies. It's just the complex conjugate of the same one at the positive frequencies. Then, Parseval's theorem. Well, Parseval's theorem tells me that this integral in time domain is the same as this one in the frequency domain. It tells me that the total energy in the data can be computed either in time domain or in frequency domain. And this Fourier transform square can be interpreted as the energy spectral density. When the noise or the signal has an infinite extent in time domain, you can still define the power spectral density, and basically you just normalize by this time. And another thing, a warning point here is like, watch out. Many authors talk or work with single-side power spectral density, and some other ones with the double-sided. So careful with conventions. Now, this is something we have to estimate from the noise itself. And we have to estimate them empirically. The simplest way is that you compute the Fourier transform for the data itself. You compute the magnitude. Basically, this is the periodogram. And if we are assuming a stationary noise, we can show that the frequency components are statistically independent. Okay. So basically, what I'm saying is that using my definition, if I want to estimate the power spectral density, I could just do it by doing this operation here. This is my periodogram. This is my estimator. Excellent. And this estimator is the so-called periodogram. It's gone off. It's gone off. It's gone off. On, hello?
Low battery. I will go and get more batteries.
Okay. I'll try to shout more then. Okay, so this is an estimator, and because this is an estimator, it's itself a random variable. And therefore, as a random variable has a mean, a variance, etc. And when we say that this is not biased, it's an unbiased estimator, it's because when I do the mean with respect to the ensemble average, returns me the value that I want. The only problem is when I compute the variance is as large as the value itself. So this is a beautiful estimator, but come on, I have a problem. The problem I can solve, and it's solved, you will have seen explained by others, it's like, if I have a data set, I can derive the PSD by just doing the Fourier transform here, or I can do something smarter. That is, to grab the data, split it into segments, compute the periodogram for each data set, and then average. And therefore, I'm going to be reducing the variance. I'll be reducing the variance by, if I divide it into n pieces, by a factor 1 divided by the square root of n. The only thing is that I would have lost is going to be frequency resolution if I've done it in this way. Another point that I have to be careful is like, oh, I have a discrete series, but I have an initial time of the observation and an end time. This is equivalent that I will have like an infinite data series in which I have multiplied by a rectangular window. And if you might all have studied Fourier transforms, if I have a product of my data with a window, basically the Fourier transform is going to be the convolution of those data functions. So the Fourier transform of a rectangular window is a sinc function, a beautiful sinc function. And therefore, imagine that I have a monochromatic signal in the time domain. Just because I'm analyzing a finite piece of data, when I'm doing the Fourier transform, instead of having a delta function, I'm going to have this. Good. That means I have to live with leakage, spectral leakage. And then comes all the story about windowing data. That I could be talking for hours and hours about windowings and different windows, and which window to apply for which searches. So the rectangular window is horrible. It produces a lot of leakage. So in some applications, some electronic applications, or even when you do study the periodic and so on, automatically the default is going to be a Hanning window. And if I want to estimate my PSD, what I will be doing is that I will be producing chunks of data that they overlap by 50%, apply the Hanning window to all of these pieces and average. In some other ones that I don't want to lose so much data, what I'm going to use is going to be tacky windows, in which basically is very similar to this. It's just that I'm smoothing the edges, because these discontinuities are horrible. They will going to give me horrible things. So things can be easy or a disaster. Basically, I have to compute the spectrum, and then depends for what problem. If I want to analyze transients that at most are going to be some seconds or a minute long, I could just take maybe an hour of data or half an hour of data of just 5 minutes, and then make the smaller chunks, and then average. When I'm looking for continuous waves that will have to search, that I will explain my signal for during months or years, clearly my noise is not stationary. I have to continually update my estimation of the PSD. I can do it with, or I do it for my problem, with chunks of half an hour, and I have to estimate the PSD from the half an hour itself. So what I have to do is, when I have done the Fourier transform, what I have to do is to do averages. I have to smooth it in the frequency domain. There was a question here.
You might have been about to answer it, but I guess I was just wondering, like, if you could describe when you would want to use a 2D window over when you would want to use a Hanning window.
It depends on the problem. Basically, for me, that I want to get all the content of the signal, and I am analyzing big chunks of data, and I want to get the most of it because it's spread. For continuous wave signal, we usually just use this top flat tacky window, minimum like half an hour long, an hour, 2 hours long, because I don't want to lose the information embedded here. It's not completely true, because there are some other people like using the power flux that do apply Hanning anyway, and then what they do is that they do the chunks overlap. It really depends on what you want and how your whole performs. I want the highest amplitude, and since I want the highest amplitude, I don't want those amplitude. I want it as rectangular as possible. In some other applications, what you care is that you don't want the leakage. And then the Hanning basically is the best you can do for preventing leakage. But you are losing amplitude.
Thank you.
Okay, and this method that I just mentioned here, to estimate by using this average of baking chunks, is called Lavelle's method. But there are many more methods. For example, there are these fear models and so on. You could just get an analytic model and try to adjust coefficients that you will be by refreshing, by updating the coefficients with the different chunks of data. Good. Okay, so basically we have my data. My data is noise plus a potential signal. And I will make life easy because, as I say, well, now we want to find signals embedded in this noise. I will make the assumptions that my noise is stationary in order not to make my life difficult. And then my Fourier components are going to be uncorrelated. And then sample average of these is basically related to my power spectral estimation. And here, I put the single-sided noise spectral density. If my data was not infinite, and if it's restricted to a certain time interval of length t, this can be redefined in this way. And usually, when we make plots, instead of using this quantity, we plot the square root of this. That is called the amplitude spectral density, and that has dimensions of an inverse square root of hertz. Okay. Now the next thing is that now we want to filter the data. When I want to filter the data, basically what I want to do is this. I will have the data, and I will want is that my data, I filter. Excellent. If the data is just over a certain observation time, well, then I will do the integral. Sorry, it's not properly written there because I did not have an equation editor. Basically, I just write this way, and depending on which book you look, you have to look at the different normalizations and definitions of different authors. You can define in this way. Okay. So this is what we do. We filter. We do this. Now, if we know what we are looking at, we could imagine that instead of multiplying by a random k function, I could just multiply by the signal I'm looking for. So what I could do is, instead of doing this operation, try to do this. If this is the signal that I think is in the data, because, in some way, if I do this operation, my intuition tells me that somehow they should be able to amplify my signal if this signal is present there. So the problem here is that I want to find which is this function, which is this filter that I have to use that really maximizes my signal to noise ratio. And what is signal to noise ratio? So it's the expected value of the filter output, y, when the signal is present, with respect to the root mean square value of the same quantity y, when the signal is absent. So this is the definition. This is the definition for match filtering or for any other test or for any other search that you might be doing. Okay, and just to point out that either we can do operations in time domain or we can do operations in frequency domain. So basically the integral that I put here, we usually like them to do in frequency domain. And if I do them in frequency domain, I can make another assumption. So the first assumption I said was stationary noise. And the second assumption that we usually said is that our noise has zero mean. So under these two assumptions, the previous SNR, it gets just written in this way. It was the average, so here we will have an x. X is n plus h. So since the average of n is 0, it only remains h. And then taking into account all the properties and the definition of the power spectral density, the root mean square value of the denominator just comes this way. Now, you can introduce a scalar product to make the notation more compact. If the functions are real, you can express it in this way, and if not, I can rewrite it in 10,000 ways. And then you have to be careful if this was just defined for real functions or not, if it's using single side power spectral density or not, or the power spectral or the full power spectral density, and if the integrals are going from minus infinity to infinity or from 0 to infinity.
Could you say a few words about the difference between the single-sided and...
Pardon?
Could you explain a bit about the difference between the single-sided and the double-sided?
Very easy. So, you define the power spectral density as I did, so that basically you will have all the content in negative frequencies and positive frequencies. Now, when the data, if you are only interested in analyzing real data, like many experiments, the data that you record is real data. As I said before, when you have real data, the Fourier transform of the negative frequencies are just the complex conjugate of the positive ones. So you have the same information in both sides. So there is no need to do the operations in negative and positive frequencies. You can just operate in the positive frequencies. And then if you know that your content is spread in both places, basically, you could just do, let me think, if I go to the definition, Sn is 2 times Pn. If I say it properly, yes. So the single-sided power spectral density is twice the double-sided. So therefore, when you do the integral over from 0 to infinity, you recover the same. Except from frequency 0, that they are the same.
Thanks.
Okay, so on rewriting using the scalar product, basically, if we do this filter, this can be written in this way, where this u functions here is my filter by power spectral density divided by 2. So basically somehow what you see is h, what we are looking for, and this is this u normalized, this u divided by its norm. So now we want to say which is the best u, which is the best k, which is the best filter. You can imagine that this we have to look for which is my unitary vector that maximizes this quantity is going to be the vector that is parallel to h. Okay? So I want u parallel to h, so I'm going to say that this is constant stand h, and therefore I can derive that my filter that I have to use, k, is proportional to my h divided by s. Fantastic. Now by using this definition, I can go back to here. I put again this definition here, and you get that the s and r square can be defined in this way. Correctly. And when we're doing much filtering, basically the statistics that one uses is simply the scalar product of my data for the signal I'm looking for. So basically, this is so-called the Wigner filter, and that was the Wigner scalar product. That is the optimal detection statistics if the noise was Gaussian and stationary. Then more things to look into this, that was via the maximal likelihood estimator. I can go fast to it because Satya mentioned it, and basically it's like if you assume that the noise is Gaussian, means that your probability distribution of the noise is going to come this Gaussian distribution. If I have a signal present, and this was data, so, and this is my signal, then the noise I can write it like the data minus the signal, then the probability distribution of having the signal is going to be substituting n by this, you expand, and then this is what you get, and then we know that the likelihood is just the ratio between the probability distribution when the signal is present versus when the signal is absent. You divide these two, and then you recover the log of the likelihood written in this way. Okay, now when we want to discriminate if we have a signal present or not, we want to basically compare. We want to compare these distributions because we are going to make decisions on them. And in some searches, instead of putting it on the row, you put it in the SNR square, and in some other searches, you do it a bit different. But basically, the message here is that you are going to have certain distribution when the signal is not there. And this distribution of your outcome of the filter will be different if you have a signal of a certain amplitude. And what you end up doing, always, in order to make a decision if you look for something or not, is to put a threshold. So if you put a threshold, and I can continue with these things or not, or I usually like it to explain in a different way. I don't see the razor. Here it is. I mean, you can think about that you have been doing match filtering, or any other thing, any other test to the data. You do whatever test, and this is your volume of possible answers. And given a test, you would like is to find how to split the answers in either saying that yes, I've made a detection, or no, I've not made a detection. Yes, this is compatible with noise. No, it's not compatible with noise, I have a signal. And basically, this is the frequentist approach for hypothesis testing. What you want to know if I have a signal in the data, and what you do is you argue against the negative hypothesis, the hypothesis of no signal. But what you want is to test, yes, I have a signal. So you will try to argue against this one. So what you have to know, which has to be your probability distribution of this when you have no signal. That this was like what it was drawn here before. And here, I don't care which is the test. My test can be the Y test, the this, the lambda test. Let's make that the test just gives you an answer, just a linear one-dimension answer. What you do is to put a threshold. If the answer is something small, that is very compatible with this, like, okay, it's compatible with coming from noise. If your answer is something very, very high, the probability that it comes from just from noise is very little, and then you say it's not compatible with noise, I have a signal. Okay? And you say it's not compatible with noise, and I have a signal, I have a signal, I've detected the signal. So this is fantastic from the frequentist point of view, because you claim you have a signal, and you have not even mentioned what you are looking at. You have just said it's compatible with noise. Okay. Now the other thing is like, if you have an idea of what you're looking at, you can have an idea. Let's imagine that in the noise you have a signal of a certain amplitude. The probability distribution of the outcome of the test has a different shape. So this would have been the probability distribution in the noise-only case, and this is the probability distribution when you have a signal. And here, I just want to put a threshold, the best threshold in order to make a certain decisions. And when I would put a threshold and I would say, okay, if it's here, it's a signal, and here it's a noise, there are several kinds of errors I can do. The first error is that imagine that it's just noise, but I got a high value. So I got a false alarm. I got a false candidate. Therefore, the probability from the threshold to infinity of this probability density is called the false alarm probability. But there could be a signal there and be weak and be below the threshold and be here. And then there's another error I can do, that I've dismissed the signal while the signal was there and I've mixed it up with the noise. So there is the second error I can do is this fast dismissal, and I prefer this. That is the zoom of this area here, in which these are my two errors. This was the other distribution, and the integral between the threshold to, the false alarm is the integral of the one from the noise from the threshold to infinity. That's the false probability. And here is the integral from 0 or from whatever was the initial value up to the threshold of the other density. And when you want to derive which is the best test, which is the best search you can do, what you want is to minimize both these areas at the same time. If you want to study some statistics, there is the lemma from the Nielsen person that tell us that the optimal test we can do is this likelihood that I've mentioned before. And as you have seen, for Gaussian noise, this quantity here was this, that was the well-known match filtering technique. Now, okay, so this is what we have to do, but another thing we can do is to maximize this quantity with respect to the amplitude. We want, if I have a signal of whatever form, I can just write the signal like whatever times A, and if I want to maximize, I can leave you as an exercise, it's very easy. Get this, substitute the H by amplitude, whatever number thing, derive equals to 0, get what is the value of A, plug it back in, and then you get that the maximum likelihood is this way. So in other words, basically they tell us for a stationary Gaussian noise, the best we can do is just to do this inner product with the normalized methods. And this is what is done when we are searching for these binary inspires that we saw. You search for all, not just one template. Now for many templates, because that was the optical statistics when you're looking for one signal. That we have the noise, a potential signal here, and this is my template, this is the output, and at the time of arrival, if these things are equal, I have like woof. Okay, now the problem is that I have to search for many of these signals, because I have to cover full parameter space. I have to search for all the possible masses, spins, or frequencies and frequency derivatives in the case of continuous waves. And basically, in the literature, you will see definitions as match, mismatch, overlap, ambiguity functions, especially the similar definitions. Then what you do is that you just do the inner product of two of these signals, normalize them properly. Sometimes between these definitions, this quantity is analytically maximized, either about time of arrival or of initial phase, and they still keep giving the same name. But basically, somehow this quantity is going to tell you how much is the loss of SNR if there will be a signal there and you are analyzing with a different template. And when you do this template, placing the templates, what you don't want is that your SNR to lose more than 0.03%. Why? Because that means that if you are having a certain reach, you could reach at a certain distance, you don't want to lose more than that. So, at most, you want to be in the 97%. Why? Because that means, if you do that, you cube it, and then you subtract. That means that you want to place them in such a way that you will not lose more than 10% of your signals. That's not the end of the story, because this is this definition that I guess not sure if Chris you will go through it or not. about much filtering, fitting factors?
Actually,
No. Oh, okay. So I'll think. So basically, this is one story that this is important for you to understand that the placement is going to be a difficult problem, as Satya was mentioning, and you have to compute this. Another story is that the searches could be difficult because the models might depend on many parameters. Or one thing is the signal, the real signal of nature, and the other one is our theoretical models. So imagine that all our signals live in this plane, but our models, if I change all the parameter space, live in a different space. And there is a distance between the two of them. And it could be that for a certain mass and speeds and so on, this is my signal, but the model which I'm using, because I'm using phenom, whatever model, or EOB, whatever model, or I'm using post-Newtonian until 3.5 p.m. or whatever, that's not the full reality. It's not completely accurate. So maybe this, it will give me a certain loss of SNR. That might be large. But if I just move it a little bit to different pointing parameters in the search, this distance is not as bad. So that's okay for detection. And then we define the definition of fitting factor, that is to maximize this overlap, match, mismatch, whatever you call it, ambiguity function, over the full parameter space. And that will really give me the distance between two families of templates. And sometimes you don't need to say that the overlap is that good, or the mismatch. What you need is to add that the fitting factor to be good. The distance, you can define it in this way, and as Satya also presented, this you can derive the metric, and this is the metric that is used for placement of templates. Of course, that's not all the story. Our data, we have to deal with non-stationary noise. It's not Gaussian, so we have to really discriminate if the signal is real or not. We will have to search if we have many tools to search if the data is consistent with the signal from some model, coincidence consistency tests, to make sure that there were no instrumental problems. And we have many things, depending, for example, if it's consistent with the model we are looking, in the case of its spiral, we can do chi-square tests. We can check other things. For continuous waves, it will be like if the signal is really following the Doppler modulation. In the case of a stochastic, if the signal is really following the expected spectrum. Then the signals have to arrive at consistent times. Knowing the distance between the two LIGO, for example, detectors, the signals can at most arrive in 10 milliseconds of differences, and with Virgo at most 20 milliseconds of difference. The signals that arrive at different detectors should have consistent properties. Either they are coming from the same template, or same frequencies, same durations, consistent amplitudes. And I can do coincidence tests, or I can do cross correlations. So I can look if the signal is the same, if I get correlation in the two data. Or I can also allow for time shifts. And more things I can do. All these we have also can validate to have used injections, software injections and sometimes hardware injections, in which we have been shaking the mirrors, and we have injected movement of these mirrors as it would be a gravitational wave signal. And we have done by injecting signal like this, and also injected continuous wave signals, are those coming from pulsars. And this has been done as an end-to-end test for everything, and for our search methods as well. Also, it has checked our calibration, and for many safety vetoes that we are applying. When we do detections, there is the significance. We have detected something, how significant that is. We want to know which is the probability that that would have not been by a fluctuation of the noise. And you have heard that we said, oh, that was a 5 sigma. What does that mean? Well, you can compute which were your probability of having observed the signal at a certain amplitude of larger. And then, when we say like this is an n-time signal, then you compare this p with if it would have come from a Gaussian distribution. And usually, in our case, and also in particle physics, when the significance is higher than a 3 sigma, we say that it's evidence, there is an evidence for things. And when it's higher than 5 sigma, it's when we clear detection. And if we don't have detections, we can put upper limits. And this, I think, is my last slide of this part that I already overdrawn what I was expecting to say. And then, well, we can also make conclusions, even from the negative answer, from non-detections. So we can always try to claim which is my strongest signal that I could have been in the data, because otherwise I would have detected with a certain confidence level. And then here I could also have another 1-hour lecture discussing the definitions of confidence levels, upper limits, with different approaches, a frequentist approach or a Bayesian approach. Because even with different concepts of or probabilities, things don't mean exactly the same. And I stop here for. So let me move to my second part of the talk, since I think it's just me and then next week Maria Sandra is going to talk about continuous gravitational waves. So, continuous gravitational waves coming from spinning neutron stars. And what are these neutron stars? Well, they come from the radial past of a collapse of a moderately massive star. They have a remnant spin coming from the progenitor, or they might have been spin up because of accretion. Generally, they have strong magnetic fields, and a small portion of them has been seen as pulsars. And if they are somehow non-axisymmetric, they can emit gravitational waves. Fantastic. So far, we have not seen any continuous gravitational waves. Okay. And there's some difference with the other transient searches, because in this case, most of the searches start after the run has finished, and all the data is there in the can. Just to point it out that we are almost finishing O2 run, but we are still analyzing O1 data. Even that, we have already put very interesting upper limits, both from known and unknown neutron star sources from this initial data. More. So neutron star is like a body, a star, which the typical mass is 1.4 the mass of our sun, between 1 and 2, or big for extreme. Radius could be around 10 kilometers radius. They are rotating between 0.1 Hz up to 700 Hz. The equation of state of decomposition is unknown. The magnetic field can vary a lot. And it could be of the order of 10 to the 8 neutron stars in the galaxies. Maybe about 10 to the 5 could have been pulsars. And of those, about 2,500 have been observed in catalog. Hopefully in the future with SKA, maybe we might have 20,000 in the catalog, but not yet. And of those, I think it's of the order of 400 are now in the LIGO band. Good. But we can see more. We could see more. Another thing of them is that many of these known pulsars, they are usually put, you will see pictures in this PP dot diagram, that tells us quite a number of interesting information. It's like this gives information about the life of the pulsar, similar to this Hensel-Russell diagram for ordinary stars. And of these pulsars that I told you that we know that about 160,000 should be isolated, and about 40,000 should be in binary systems. This diagram has a lot of information just from these two observables, P and P dot. From there we can estimate the age of the pulsar, magnetic field, and the spin down derivative, how much energy has gone into spin down. We have a lot of interest in trying to detect these gravitational waves because the physics of these stars is poorly understood. after so many years, we have no clue why they are pulsating. Well, pulsating is because they are pointing to you, but why is this emission? As I said, we don't really understand the interior properties. Maybe some in the audience here know more about me about them. And they could even, if we call them neutron stars, they could be more exotic. They could even have quarks. So basically the structure of a neutron star is that it has a crust, neutron liquid interior, and a core. And even in the crust you have like two layers, an outer crust and an inner crust. Of these 10 kilometers, the crust is just 1 kilometer in length. Then you have a core that may be just 1 kilometer in length. In the crust, there are two parts. The outer crust, that's solid, it has a lot of iron. The inner crust is like a lattice of neutron-rich nuclei. Fantastic. And in the fluid part of the interior, that spans basically like 8 kilometers, near the crust, there's some neutron fluid that can penetrate into this part of the lattice that rotate at different frequency rates, and they can produce glitches, all of things. And about the core, I don't know. Could be many interesting things going on there. Now, if we just have something axisymmetric, oblate star, that would not generate any gravitational waves because there will be no quadrupole changes. And for those that started like me in the Middle Ages, starting perfect fluid stars, perfect fluid stars cannot have non-axisymmetric distortions. So you say, well, then it's game over. No, it's not game over because real relativistic neutron stars can have deformations that are supported either by the stresses in the crust or by the presence of strong internal magnetic fields that put this pressure. And they produce some deformation that we quote until this quantity that is this ellipticity. That basically is the difference of these moments of inertia. Excellent. So the important question for us is how large this distortion, this epsilon can be. And there have been studies telling me like the maximum distortion, the maximum ellipticity is related to this breaking strain, so maybe of the order maybe 10 to the minus 7. But there have been more modern studies that has told us that, okay, maybe this sigma here can reach 10 to the minus 1, so that this can be a bit larger. That for normal neutron stars, if you go to more exotic things, if you have some quark stars, there's another studies that can tell you, well, the deformations can be until 10 to the minus 4. Okay, good. Apart from this deformation, neutron stars could also emit gravitational waves due to, for example, unstable fluid modes, free precession, magnetic stresses, or accretion that induces deformation. So basically the message here is that we have different mechanisms for which a neutron star could emit continuous gravitational waves. As I said, because there is some deformation, we usually put it as a mountain. This is not a mountain, just a deformation. Because these mountains could be because of the magnetic fields on the inside. It could be isolated or with a companion, and it could be accreting matter from a companion. So that would be fun, yeah? One neutron star, a pulsar in a binary. So it emits because it's a neutron star, and it would also be because it's a binary. And then we have different modes. Now, let's look into the strain of these signals. And for that, I really recommend a review article written by Reinhard Prix that was published in Springer Lecture No Series, in which basically derive what you have seen me in the lectures before, which is the luminosity. You derive this luminosity, and you look into this equation. What is funny here is that this number, c to the 5 divided by g, this is of the order of 10 to the 52. This is the reversal radius, this is the rotational velocity at the surface. And now if we focus what are this number for compact objects, or objects that have a radius closer to this reversal radius, that are rapidly rotating, so you can put here the velocity of light, think of black hole or neutron stars, they are going to emit enormous luminosity, even for tiny amounts of epsilon. Now, the problem is that space-time is stiff, and even this large amount of energies, the amplitudes are small. So the most typical case, my triaxial neutron stars and my bumpy neutron stars, that has a certain rotation frequency nu, around a certain axis, that's going to meet a continuous monochromatic signal at twice the rotational frequency, that is going to have an amplitude characterized by this equation here, given the distance of the source. So the amplitude is inverse proportional to where the distance of the source is. It depends on the rotation, it depends on the ellipticity. So if we now put an example for a strongly deformed, so 10 to the minus 6, close by, distance 100 parsecs, in our galaxy, or we're always in our galaxy, and very close by, at a rotational frequency of 50 Hertz, so it means emitting at 100 Hertz, this is giving us amplitudes of 10 to the minus 25. Fantastic. What we have been observed, the first detection was 10 to the minus, the peak amplitude was 10 to the minus 21. So I guess it gives you the idea that for this optimistic case, this is a much weaker signal. Now, if we do much filtering, as I explained before, the signal to the ratio can scale like this. Amplitude, square root of the integration time, or the duration of the signal. Then this is the single side power spectral density, and now we can have, okay, what were the characteristic sensitivity regimes for our advanced LIGO 01? Oh, okay, in this sweet spot, 10 to the minus 23. Okay, that means like, oh, for GW150414, that was having an amplitude of 10 to the minus 21, it lasted 0.2 seconds, the SNR, there we get 24, fantastic. Now, if let's put the more visual in the smaller SNR, maybe 8 or maybe smaller, what would be interesting? What would be my threshold for detection? Let's put the value of SNR. Let's put the value of my amplitude here. Let's put the value of my noise level. It means that for me, I need integration times of days, months, or years to observe these signals. And then there's another quantity that might appear in some other talks as well, that is the depth of a certain search. That is what we characterize like different methods have different depths. And the depth is basically the square root of the amplitude spectral density divided by the amplitude of the signal. So we have to design methods that have depths, maybe of the order of 100.
Excuse me?
Sure?
How robust are these long-term measurements against like these glitches that neutron stars have when they like spin suddenly faster a bit and stuff?
Basically, for when we do these long-term integrations, I will mention that we do coherent searches and other searches. For the other searches, we don't get so much, but for the coherent ones, we do create a lot. And basically, you need precise timing information, precise ephemeralities, and good connections with your electromagnetic, X-ray, and radio, or whatever astronomers, because they have to tell you when it glitches. Because if it glitches, you are going to have like this continuity in the phase and the frequency, and you have to cut your integration time. Otherwise, if you do much filtering, you will lose it. So you need that information. Okay, so basically the message is that if I want to be able to detect this gravitational wave emission, this really has to last for a long, long time in order to be able to dig from the noise. And this is what characterizes the class of continuous gravitational wave signals. And we have large uncertainties because we have no clue about the range of the epsilons we should be able to look at. I mean, maybe 10 to the minus 12. In the most optimistic and exotic objects, 10 to the minus 4. And we have also uncertainties in the polypole moments. Even we also mentioned like, okay, now we are looking for neutron stars. This is not, of course, not the only emission that neutron stars have. They can also produce burst-like emission due to F modes, P mode oscillations excited by a glitch, or acoustic torsion modes and so on. But I'm all interested in the continuous wave radiation. So as I said, that there are different mechanisms. The non-axisymmetric distortions are characterized by this ellipticity here, and neutron stars that are in pairs in binary systems that can accrete, they can have large deformations. In these cases, when we have deformations, they emit at twice the rotational frequency, but internal strong magnetic fields that could also produce large deformation would then result also in continuous emission both at twice the rotational frequency and at the rotational frequency. There could be several fluid instabilities. The most well known are the R-modes, toroidal modes with Coriolis restores in force. And then the frequency at which they will be emitting will be a 4/1 the rotational ones. Or a neutron star could have like a rotation axis that is different from the symmetry axis. And that there will be precession, that the thing will be wobbling. And depending on the wobbling angle, I can also have gravitational wave continuous at different altitudes. But basically, we would almost refer always to this first mechanism. It doesn't matter. This, in all the cases, they are going to be basically a continuous wave, almost monochromatic. Another concept that I want you to remember here is these spin down limits that we always mention. From those known stars in which we have measured F and F dot, we know that it's losing energy. So we can compute which is the rotational energy lost just from the observations, from the frequency and the frequency derivative they have. Now, assuming a certain deformation, ellipticity, we can also compute which is the energy emitted into gravitational waves. Now, what are these spin down limits? The spin down limits is, now let's assume, that is wrong, that all the rotational energy lost will go into gravitational waves. If I say that this is equal to this, then I would be able to derive which is my maximum value of epsilon. And when I have this epsilon, I can just put it back in this equation, and I can get what is my maximum value of amplitude of the signal. And this is what we do. This is what we do. So assuming that we are at the spin down limit, so that all the energy will go into gravitational waves, that is not true because it goes most of it in electromagnetic waves. Then we have which is the maximum deformation. You just here, and then now substitute this in the equation, and which is the maximum amplitude. And these are the plots we have. So this is for H0 versus frequency, and ellipticity versus frequency. And here you can compare with the sensitivity of your detectors for a certain integration time. And I guess this might be for 1 year integration time. This was for Virgo. This will be for design advanced LIGO, eventually for ET. How many we have a chance of those at time catalogs to see? But the point is that we have no clue, because we have no clue how large these ellipticities can be, and we have really no clue how much of the energy can go into gravitational waves. So it could be here, or they could be farther down. So we really have no idea of how many signals we can expect to detect in this first year of the advanced detectors. So we really have to know more about these equations, these neutron stars. The only thing I can say is that for the initial detectors, 70% of the known pulsars go in our band. Eventually, for advanced LIGO, it's increasing, and it will increase more as we broaden the frequency band of the detectors. If we would detect gravitational waves from this continuous neutron stars emission, and at the same time, if there will be electromagnetic observations, there will be a lot of information we could derive, because we could observe the rotational frequency and the frequency in which we have been detecting things. So depending if it's twice the rotational frequency, we know that it's a triaxial neutron star. If it's almost but not quite, we'll have maybe information about the crust, the core coupling, etc. If it's almost at the rotational frequency, we'll know that precession was important. If it's at 4/3, oh, we know that, oh, we have emission from Arnold's. If the electricities then will be very, very, very high, we can potentially narrow down equations of states. If we have multiple detections that can get information about the electricity distribution, then we can constrain models. And we could even say like, oh, do you have different models for normal or millisecond pulsars? Of course, we can always compare the phase of the electromagnetic pulsar timing and the phase of the gravitational wave signal and see if it will be really low or not, and use them to the test of GR. Let's skip this. So let's move to the signal. As I said, my signal is boring. It's very easy. It's an almost monochromatic signal. So you have a certain amplitude, could vary a bit in time, and a certain phase, but nearly monochromatic. Because it's nearly monochromatic, my signal to noise ratio squared, that we were discussing before, it just is like this integral. So basically the message here is that this integral grows like T. So S and R grows like a square root of time, if I can do much filtering. Now, this boring, almost monochromatic signal, of course, can have some spin down. It will have some spin down because it's losing energy. So we will have to have frequency derivatives. So we are going to have some phase evolution, small and slow, but we have that in the source frame, or if you want in the solar system barycenter frame. But we on Earth, we will be on a detector that moves. So the phase as we will be receiving is going to be, okay, you just expand, you Taylor expand, and you put all the derivatives. But you have to be careful, because this T, you can expand with these derivatives at the time of arrival of the signal at the solar system barycenter. But on Earth, the time at Earth is different from that. That means that even if it was the signal completely monochromatic, at Earth, the signal is going to be Doppler shift. And then you can apply the typical Doppler shift formula, and how much gets Doppler shift depends on the frequency itself and the relative velocity between the detector and the source and the sky location of the source. Not just that, you saw the first plus that I showed you about the antenna pattern. My detector, I have the source there, but the Earth rotates and moves around. So I'm not going to see the same intensity of these antenna patterns. I'm going to have the amplitude modulated because of that. So these things will change in time. Therefore, my signal, that here my polarization, this is valid for all the cases. And now what are these characteristic amplitudes here? That really is going to depend for which was the emission mechanism that we're emitting. If we go for the triaxial at the start, this will be the shape, and if not, whatever, change a little bit. And this is the signal as received by my interferometer. That is going to depend on the sky location, the polarization angle, the inclination angle of respect of the slot of light, some initial phases, and what we call the characteristic amplitude of the signal. That depends on this electricity. So the signal, as I said, the signal is almost a boring monochromatic signal, but received on Earth is Doppler shift. So this is time, this is frequency. So this variation in frequency is a relative variation of 10 to the minus 4 over 1 year, and a relative variation of 10 to the minus 6 scaling with the frequency over the day. Because you have two characteristic velocities, the rotation and around the Earth. Of course, this is what if the signal was isolated, monochromatic. And what do I have to finish? In a quarter of an hour or in half an hour?
I think in 20 minutes.
How much time I left?
It's quarter of an hour, right?
A quarter of an hour. Okay, and then you have many more complications if you have the signal in a binary, because then you have to add all the Doppler things. Okay, so I will skip that. Okay. The funny thing is that of this business is that in this case, I only need one interferometer to detect the signal and to locate the signal in the sky. Because thanks to all these modulations, and because my detector moves, basically makes like if it will be a network, like it will be a LISA light detector for their own sources. Now, the searches that we can do, there are some sources that we know, and sources that we don't know. So we will only have a chance to detect a neutron star if it's close enough, if it's deformed enough, and if it's spinning in a rate that it's in our frequency band. And I can decide to look for those that are in catalogs, that is going to be very easy to look at, like not that many, or to start to search for the unknown, because I said there are many neutron stars in my galaxy.
What's a typical range for continuous waves from neutron stars? Like how far away can you see them?
Depends on the method you use. It is going to depend on the sensitivity of your detector. At the end, I have things like, it depends. So if you are at 10 parsecs or 100 parsecs, that it will give you more range depending on the elasticity. So the closer you say you look, I can put you more stringent upper limits on the elasticity, and at the farther away, I can tell you less stringent deformations.
But it's
No, the rest.
So it's on order of 10 to 100 parsecs instead of like megaparsecs?
Ooh, I can only say how, these are so weak. I only have my chance to see the signals from my own galaxy. I am not reaching not even the galactic center. But that's what, 8 kiloparsecs away. So I'm talking about 100 parsecs, 10 parsecs, depending on the search method. So basically, when we do the search, the signal is going to depend on a number of parameters. Position, frequency derivatives, orbital parameters that can be known or unknown. The signal also depends on initial phase, inclination phase, polarization, and amplitude. And what we are lucky is that we don't have to search explicitly for them. We don't have to search for these. And these can be known or unknown. And depending on how much information I have, there are different algorithms that have been developed to search for different things, depending on how much amount of information I have. And of course, depending if my signal is isolated on a binary system. And basically, depending on the amount of information I have, we separate the neutron star populations. So for completely non-radio or X-ray pulsars, in which we have everything, we have the location in the sky, frequency and frequency derivatives, is one category. For those that are completely unknown, not yet cataloged, we have to do blind searches. We have to search for everything. Then there could be something like accreting neutron stars in low X-ray binaries, like XLX1, in which we know the position, and maybe some orbital parameters, but we have to look the rest, frequencies and spin deltas. Or we could have a non-pulsating neutron star, in which we know the position, but we have to search for the rest. So basically, these are the different search categories, different search populations, and my categories of searches then are divided this way: targeted for what is all known, blind for completely unknown, directed searches when we point in a certain location in the sky, and for all of them, our cornerstones is that we have to design searches that are sensitive enough. They should be robust with respect to the signals and uncertainties that we have, or towards instrumental noise, and the search should be feasible to be done computationally. So all these searches are going, except the target ones, computationally bound. We can use coherent methods, much filtering methods, that will require accurate prediction of the phase evolution of the signal, or we can use semi-coherent methods in which we only need is a prediction of the frequency evolution. Or we can mix them in hierarchical searches that again they will be introduced to you next week. What we choose, which method we choose for which search, is going to be how much it costs computationally to do the search. Yes?
How do you do directed searches with our decent parameters? How do you do directed searches? Because I feel like, how do you know it's coming? Like we have rough sky localization, right?
Yes, you could say, for example, galactic center. For me, just one point in the sky.
Okay.
Or you could say, oh, somebody passed you a supernova remnant, and you say, oh, that could be interesting. Maybe there is a pulsar inside there. So you point to that supernova remnant. But you still will have to search for F's and F dots.
So you will have to do that in the data analysis itself, right? Because we.
Of course.
Oh.
You will have to. It's the same data from where we look for stochastic, binaries, and neutron stars, supernovas. You all do that in software.
So you essentially like restrict the parameter estimation to certain theta and phi values only and run that.
We are noise dominated. We are not signal dominated, so we don't have to worry about interference without a signal.
Okay.
So basically, these are the zoo of searches, the target searches. Target searches will be based with machine learning techniques. Of course, we need very accurate remedies to search for them. Narrowband searches, in which we could allow some mismatch between the information that is given to us. So we could just look around the information that is given. We could do wideband directed searches, or we could search into systems that are in binaries, or we do blind searches. Of course, the message is, the more information you have, the easier it is to search for it. Coherent searches, where as I see, the signal to noise ratio increases like square root of time. For semi back, if I have no clue what I'm searching for, the computational cost can simply blow up, depending on how many derivatives or scale locations and so on. I mean, the cost can scale easily as 10 to the 7th. And more will be explained also next week. But if I just click the data into chunks and I combine them incoherently, if I combine them incoherently, it does not grow like number of chunks to square root, but to 4th square. But more information next week, and I think it's covered by the sun. Anyway, and we also have the problem of the target. We have to tile now, we have to put how far we have to search in order not to lose the signal. This is also another very interesting problem because we have to grid sky locations, frequencies, frequency derivatives, and orbital parameters. And then we just have seminars on how to derive these matrices, depending also on the search you want to do. And for all these methods, there have already been a number of results. These are the most recent published results. And to have electromagnetic information is extremely relevant. For the target searches, we really need accurate timing. If it is, information about the day glitch, and if not. If they are in binaries, if they could give us more orbital parameters, that would also be excellent. Or somebody could now run frequency emission in some cases. So basically, we really need more timing for pulsars to do these kind of searches. And not just that. If we would detect something, if there will be electromagnetic follow-ups of signals, then we could do a lot of science, because then we could check what information we have. Searches that they have been performed. Okay, let's go for the target, the known ones. For the known ones, this is the latest results, in which there are now 430 known pulses in the band, but we only follow 200 of them. We only follow for target searches those that really we have very, very good and precise information. And there are several methods. The Glasgow people, they have been developing for many years the time domain Bayesian method, and there are others. And what is remarked is that for 8 of the pulses, I've already beaten this spin down limit that I was mentioned before. For crab, the energy lost is less than 0.2% of the rotational energy. We know how to gravitational wave. For Velas, we know that it's less than 1%. And the most stringent upper limit in amplitude is 1.6 10 to the minus 26. In ellipticities, this vary depending on which pulsars. But basically, putting upper limits in ellipticity, then we can get how large the size of the mountain can end up being. It's a few centimeters for carbon velvet, can be much smaller. I get more information. Let me go to models. So I present in 5 minutes several models, several ways to search for things. And I'm going to present 2 searches here that were done for the first paper of S1 for LIGO, time domain Bayesian analysis, and the frequency domain frequentist analysis. The frequentist domain method based on match filtering techniques, but this was thought and derived in order to be like a model for a more complex search of this hierarchical search, to search for unknowns. And the time domain that was really derived for doing these targeted pulsars. And this one was very efficient to handle missing data or have some pictures, etc. So let's go to this frequency domain. F statistic. It's just one shooting. It's what basically I said before. You have signal, and this signal, the funny thing of this F statistic is that we were right. So if this is my amplitude, the F with the H plus, F cross, H cross. Now we basically do some little maths. And we were writing to amplitude parameters and Doppler Parker parameters, on which amplitude parameters are the A plus A cross, polarizations in initial phase, and all the other ones. So if you just do some math and you split the F's into a little bit, and then your H, you split it a little bit, you combine them together, now you have my amplitude parameters and my H parameters. What do? I just maximize analytically with respect to my X to the match filtering. So this, in match filtering, this is my log of likelihood written in tensor way, can be written with this expression. I can derive with respect to the A equal to 0, derive the maximum likelihood of the A, put them back in, and then I get what is this F statistics, because how many level letter F, so twice F, what this quantity that I have to do. So this is the quantity we have to do here, and for every time I do a search, I'm going to have about this F. And the story will be the similar one. I do a target search, I get a number, whatever I filter, I get a number. I have to put a threshold on this number, and if it's higher than a certain amount, I make a detection, and if it's low, I don't make the detection. Oh, well, if everything will be Gaussian and the stationary noise and so on, it will be fantastic. I know exactly what is the probability that is the distribution of my outcome. My outcome is going to be a chi-square distribution with 4 degrees of freedom with a certain non-centrality parameter that is going to depend on the amplitude of the signal. Fantastic. And from that, I can derive then these distributions that I was telling you. Okay, so depending on where to put the threshold, I can tell you, oh, given certain pulsar, I know where I want to put the threshold. And if that's not that relevant, I can put upper limits. And my upper limits is that I'm going to have this distribution. Of course, this distribution will vary a lot. Will vary depending on the amplitude of the signal. Bigger signal, stronger signal, stronger signal. And if I want to put like a frequentist 95% upper limits, I will have to find which is the amplitude that should be in the signal such that this area here would be the confidence level that I'm requesting. So if I want a 95% confidence level, I would like that from the threshold that I'm putting up to the end, this will be whatever I want. And this is a frequentist upper limit, and this is what was done. We analyzed the data, we got different values from different detectors, we didn't see a thing, and then by doing many Monte Carlo injections, because we are chi-square distribution so and so, but my data is not Gaussian, my data is not stationary, and I'm forced to do Monte Carlo injections to really characterize this distribution, because it's not my theoretical one. So this is one way to do the analysis. Another one way was the time domain Bayesian analysis done in the time domain, and this is quite interesting because it's basically based on heterodyne in the data. Heterodyne in the data is that it's just that basically you will multiply by the phase, well, by the signal you expect, but just changing sign. Basically, you will just move to zero frequency. And of course, for that you will require all the precise information because what you would like is to correct for the same model of the phase. So basically, this is usually we do it in two ways. First we do, or in the Middle Ages was done, first we were doing a quasi stage, just by knowing which is the rotational frequency of the source. And you will just heterodyne that by the fixed frequency. And we will pass from this 16 kilohertz of sampling rate. So you heterodyne, then you bandpass. And since you bandpass, then you can downsample the data. And then from having 16,000 points per second, you are going to have just 4 samples per second. And then the second stage was a refined heterodyne, exactly using all the ephemeris data, the precise scale location and derivatives, and all the time units and so on. You put that in that model, and then you will correct for the rest. You will again bandpass the data, and then you can put it down to just 1 sample per minute. So you have basically reduced your data a lot. And then what you are left is that your data will just depend on your unknown parameters. And then you are just basically facing the very typical Bayesian parameter estimation problem. You just have to find which is the posterior probability distribution, assuming a Gaussian mass. So it's just the typical thing. And the typical thing when this comes is like, okay, I can easily deduce this from the data, my likelihood. This is the data that I say, my model, the standard deviation. I can assume some priors, they could be uniform, and I can get my posteriors from my unknown parameters. And if I'm only interested, let's say, in the amplitude of the signal, I can marginalize the rest by integrating all the other parameters, and then I can get the probability distribution. So that's what we do. And I can do it just with one detector, or the likelihood, I can compute it by doing coherent analysis of different detectors as well. And basically, I can have an outcome of the posterior probability distribution. If you see something like this, I don't see that there is any detection of anything. I can try to derive and set up a limit by finding which is this value here, that this area is going to be my 95% confidence level. And this is the typical thing then. But for example, if you have been a signal, this distribution, the posterior, will have peaked at a certain value. And this will be then my most probable value that I will have made a detection. So in order to make a detection, you should have this distribution that has a clear maximum, clearly separated from zero. And these were the things that were done. So I basically have overrun. So these were like based on maturity coherent techniques. Semi-coherent techniques, well, what you do is you spread, you have your data flat, you do chunks into pieces. If they don't chunk, you do a coherent analysis, or if the chunk is small enough, you just need to do a Fourier transform. And for each Fourier transform you done, you have frequency and you have time. And all the methods that have been developed, you just want to trace the frequency evolution of the signal. And there are many ways you can trace, and there were many methods. Either you were just adding the power, or normalized power, or one method I've used is the half transform, in which I just basically, I have my maps, my spectrogram maps, my time frequency maps that are very colorful. I convert them in black and white, ones and zero, and I just zoom traces. And I think then, unless people want, I just skip all what I have on half transform, because I have completely done my time. And then if you want, it doesn't matter. If you want to know about one of these methods, just ask. I don't have. Basically, it's like we have done searches, we have done almost kind of searches from blind searches. The searches have improved a lot. These were put out 2 weeks ago, covering up to almost 500 hertz. And with this analysis, basically you can say that we can exclude the existence of neutron stars with electricity higher than 10 to the minus 5. 1 kilohertz from there, spinning frequencies of, let's say, 200 hertz. We also have power up to 2 kilohertz, and there are plots like this, very complicated with frequencies, frequency derivatives, in which if you, let's say, fix a certain distance from our upper limits, you can basically exclude or see up to which electricity you will be able to reach. So how far away we can reach, trying to answer your question, well, it depends on the frequency, the distance, and this electricity. That is all. So, we have got no detections. There will be many results that will come out very soon. And there are lots of physics and astrophysics that one can do with continuous gravitational waves. And we might be the next one detecting things. Thanks.